So the first thing we're going to do is we're going to scroll down, and you're going to find to draw a segment. So we're going to draw in our segment here. AB is fine. And with that segment, what we want to do is to draw a perpendicular bisector. So here under construct, I have perpendicular bisector. It says to select 2 points or one segment. So I can either select the segment AB, that's fine, or I can select the 2 points AB. Note that if I select one of the points, I could select a different point, and it would give me a perpendicular bisector at that point, but I'm going to select A and B. And then I'm going to also put a point at the intersection here. Now, given that it's the perpendicular bisector, this does mean a few things, right? So since it's perpendicular, that means that the angle that is formed here, I'm going to put a point on the perpendicular bisector, that will just give us the ability to measure the angle for now. So if I measure my angles, and that's the angle bisector, sorry. If I measure my angle using the angle measurement tool, you should do this as well. And go DCA and BCD. And we see that both of those angles are in fact 90 degrees. Now, if you've forgotten, the thing that shows up in front of the angle measure here, those are just the Greek letters alpha and beta. The second thing here then is, what does it mean for it to be a bisector? Well, if it's a perpendicular bisector, it's perpendicular to the segment and it bisects the segment. So what does it mean to bisect? It means to cut into two or cut in half. If you cut something in half, the two things that you have cut should be the same length, and we see here that they are. Now yours may have more decimals than this. If you don't want that many decimals, you can change it in the settings, but you can also have those, that's fine too. All right, so there is a discussion post that you should be posting some stuff about this on as we go. So you might be pausing and deciding some stuff here. So here, I think there's a question on what is a perpendicular bisector, and you should be able to answer that already. And here I think it also asks, well, what do you think is true for a point on the perpendicular bisector? So take a minute and actually look at that, pause my video, think about it a little bit, and try to get on that, right? So hopefully you did spend some time. Maybe you did, maybe you didn't come up with anything, but sometimes it's nice to put in a few extra things. So we did this once or twice last semester. As we're trying to discover stuff, we might throw in some more pieces here. So I have AD and BD. And you should think to yourself, well, does it look like anything's true about those two segments? And if so, why do I think that they're true? So if it's not obvious, those two segments appear, at least even from a measurement here, that they have the same length. And even if I move this, and you should do this on your diagram, even if I move this, they stay the same. Now, this should make sense to you. This should be somewhat obvious. So we worked with proving triangles congruent last semester, right? And here we have AC and CB congruent. That's one pair of sides. We have a right angle in both of them. And we have CD, sorry if it's unclear, CD congruent to itself. So we have a side and a side with an angle between. Happens to be a right angle, so we could do this two different ways, and the same on the other. So this is, we could say side angle side. technically leg is a little bit better. And since we could prove the two triangles are congruent, therefore AD and DB have to be congruent by CPCTC. So note that this is a proof that we could have had last semester, but it proves something different, which is a point on the perpendicular bisector. So there's a question that asks what's true. The second question tells you to write it as a conditional statement. Your conditional statement might sound something like, if a point D, is on the perpendicular bisector, line DC is the perpendicular bisector of AB, then it is what to the two endpoints, right? It is the same distance, the same length to the two endpoints. When things are the same length in geometry, we typically use a different word. So typically the word we'll use is equidistant, right? So that would be a conditional statement that you might want to write there. You could theoretically write about the two triangles being congruent, the two triangles being formed being congruent. Just saying they're right triangles is a little bit weak, given that, of course, they're right because of the perpendicular bisector. At least saying triangles makes sense. This is a theorem that we have here in section 5.1. This is trying to discover them a little bit differently to show you why they work. So the theorem here is called the perpendicular bisector theorem. Again, the perpendicular bisector theorem says if a point is on the perpendicular bisector, then it is equidistant to the endpoints. Now, there's more questions than that. I believe one of the next ones has to do with the converse of that, right? So it asks you to write the converse statement and asks you the truth value of the converse statement. So what's the converse and is it true? Remember, truth value, seemed like we were still a little bit off on it last semester, is just whether the statement is true or false, right? So write a new conditional statement, converse, flip the hypothesis and conclusion, and you would write it there. Your diagram, again, should look something like mine, but obviously your lengths may be or should be different. If you have the exact same ones, then you tried a little bit too hard to make it like mine. You're going to take a screenshot of this and post it in the screenshot part. This goes separately than the discussion. All right. If you want to, you can follow along and do any of the other ones that I do with me. However, this is the only one that you're required to do here on GeoGebra with me. So we're going to do 3 more things, but of those 3 more things, again, the only one that you have to have a screenshot of is this one. So triangles are down here in polygons, and so I can draw a triangle. And what I'm going to do with the triangle is I am going to put perpendicular bisectors on each of its 3 sides. So I've got one on AC, perpendicular bisector on BC, and perpendicular bisector on AB. Now, make a note here that these 3 lines intersect. I'm going to change up my triangle a little bit here. All right, so notice that they intersect. So if 3 lines, this is not just in a triangle, just in general, if 3 lines intersect at a single point, then those lines are called concurrent, C-O-N-C-U-R-R-E-N-T, concurrent. And the point that they intersect at is called the point of concurrency. So D is a point of concurrency. This specific point of concurrency is called the circumcenter. So the circumcenter of a triangle is, well, it's made up of the perpendicular bisectors, right? And so if we look at it, D has to be equidistant. So if we're looking at it being the perpendicular bisector of BC, D has to be equidistant to the endpoints. Well, the endpoints are the vertices. In other words, the distance from D to B and D to C must be congruent. Now, given AC, D being on the perpendicular bisector of AC, must be equidistant to the endpoints. In other words, AD and DC must be congruent. Again, in other words, AD, DC, and DB must all be congruent. Those lengths must be congruent. So, why is it called the circumcenter? This is interesting. It actually kind of fits with what it should be. So, circum is a word that we should recognize from other places, like circumference, or possibly even circumnavigate. And there are a number of other places that it come up. So here, let's think circumference, right? Circumference is to measure the distance around, well, not necessarily measure, but it is the distance around a circle. So it's around, right? Around. So it's the center, circumcenter. This is the center that we can draw a circle around the triangle. So we could do it this way, go out to a single vertex, and notice that it goes through A and B as well. And this makes sense because AD, CD, and BD, these lengths to the vertices, are equidistant, making them radii of our circle. So again, circumcenter, because you can draw a circle with a center at D going through points A, B, and C. Two last things here about the circumcenter. So one is just where it lies in the triangle. So we've kind of seen this already, right? Here, if we had to classify this triangle by its angles, it would appear, without actually measuring it, that it is probably an acute triangle. And notice that in an acute triangle, the circumcenter happens inside the triangle. If I make this triangle a right triangle, we would note that the circumcenter happens on the triangle, and specifically on the hypotenuse of the triangle. And lucky for you, because I forgot about this in class actually, not only is it on the hypotenuse of the triangle, this part I remembered, because the segment here to AC is the perpendicular bisector, it's on the midpoint of the hypotenuse. And then lastly, note that this is a future kind of thing. The right triangle here does something special in our circle in that it cuts it in half, and this is a diameter. And this actually happens with every right triangle that a circle can be circumscribed about. So that's a right triangle. Lastly, we have what happens if we go obtuse. Angle ABC is obtuse, and it happens outside. So a few final thoughts here on circumcenter. Again, obtuse triangle, circumcenter is outside. Right triangle, it's on the midpoint of the hypotenuse, and acute, it happens inside. The perpendicular bisectors of a triangle intersect at a point of concurrency called the circumcenter that is equidistant to the endpoints. Again, circum means around, so it makes sense that you could draw a circle around, and that the point then would give you equidistant to the vertices because they are made up of the radii of this circle.